Welcome, JEE aspirants. Today, we're building your complete toolkit for wave optics. We're going to move from the core concepts all the way to the strategies that will help you win on exam day for both mains and advanced. So let's get right into it.
So here's our game plan. We'll start with the absolute foundation, Huygens principle. Then we'll get into the big phenomena, interference and diffraction. After that, we'll arm you with a formula toolkit, show you the common mistakes to avoid, and then we'll wrap it all up by solving a real JEE problem together. Okay, let's dive in. You know, everything in wave optics, and I mean everything from reflection to diffraction, it all comes back to a single powerful idea from Christian Huygens. Now, this isn't just some random definition to memorize, okay? Think of it as a tool. It's the key that lets us predict how waves are going to move and spread out. It's actually the reason we can explain why light reflects, why it refracts, and even why it bends around corners. To really get this, just picture a wave front moving forward. Now, imagine every single point along that front suddenly sprouts its own tiny little wave. We call these secondary wavelets. The next wavefront is just the line you get by drawing a tangent to all of those little wavelets. That's it. That's how we can visualize a wave moving forward. So we know how waves travel, but what happens when two waves overlap and meet at the same point? Well, this brings us to one of the most important concepts, perfectly shown by Young's double-slit experiment, or YDSC as you'll always see it. This setup is absolutely crucial for the JEE. You have light coming from two coherent sources, S1 and S2, and they interfere with each other. What you see on the screen is this really distinct pattern of bright and dark bands, which we call interference fringes. So what's actually happening here? Well, the key to everything is the path difference. If the waves arrive perfectly in sync, in phase, they build each other up and you get a bright fringe. We call that constructive interference. But if they arrive out of sync, they cancel each other out, and you get a dark fringe. That's destructive interference. It's as simple as that. Okay, so we've seen what happens with two slits. But what if a wave only passes through one single narrow opening? Well, that gives us a whole different phenomenon, and we call it diffraction. Now, it's really easy to get these two mixed up, so listen close. Interference comes from multiple wave sources combining. Diffraction comes from a single wave bending around an edge. The patterns they make also look totally different, which is a big clue. This formula is your key to understanding diffraction. But here's the interesting part. This formula actually tells you where the dark fringes are, the minimums. And by finding where that first dark fringe is, we can figure out the width of that big, bright central maximum, which is the defining feature of a single slit diffraction pattern. All right, time to build your formula toolkit. These are the equations you just have to know. Think of them as your weapons for exam day, letting you solve problems fast and get them right. This one is non-negotiable. You have to memorize it. The fringe width, beta, tells you how far apart any two bright or dark fringes are. Trust me, you're going to need this for almost every YDSE problem. This formula looks a little scary, but it just tells you how bright the light is at any point, and it all depends on the phase difference, delta phi. Now, for the JEE, the intensity from both slits is usually the same. In that case, it simplifies to something much nicer. I equals 4I1 times cosquared of delta phi over 2. You should definitely remember this simplified version. Look, knowing the theory is only half the battle. You have to avoid the common mistakes that everyone else makes under pressure. That's what separates the top rankers. So let's go over the traps that cost you marks. We hear this question all the time on student forums. The trick is to really solidify the connection between path difference, which is a physical distance, and phase difference, which is an angle. Let's make that crystal clear right now. Okay, there are two huge traps here. First, units. Wavelength is almost always in nanometers, but distances are in meters. You have to convert everything to SI units before you calculate. It's such an easy way to lose marks. Second, using the wrong formula. Don't grab the single slit diffraction formula for a double slit interference problem. Always check what the question is asking for. Theory is great, but applying it is what really gets you that rank. So let's walk through a typical JEE level question, step by step, and see how all of these ideas come together in practice. So here's our problem. We're told the maximum possible intensity is I0. The slit separation is 5 times the wavelength, and the screen is 10 times that distance away. The question is, what's the intensity at a specific point on that screen, right in front of one of the slits? Okay, our first job is to figure out the path difference, delta x. The point is in front of a slit, so its position, y, is just d over 2. We plug that into our path difference formula, delta x equals yd over d. We substitute the values we know, and after a little algebra, it all simplifies down beautifully to a path difference of lambda over 4. Now that we have the path difference, we need to convert it into a phase difference, delta phi. And there's a simple relationship. A path difference of a quarter wavelength, lambda over 4, always corresponds to a phase difference of pi over 2 radians. Finally, we can use our intensity formula. We'll use the version that relates the net intensity to the maximum intensity, I naught. We plug in our phase difference of pi over 2, which means we need to calculate I naught times the cosine squared of pi over 4. And we all know that the cosine of pi over 4 is 1 over root 2. When you square that, you just get 1/2. So the net intensity at that point is I naught over 2, exactly half of the maximum intensity. And there you have it, a perfect application of our entire toolkit.
So to quickly summarize the absolute key takeaways from all this: 1. Master Huygens principle. 2. Know the YDSE conditions for bright and dark fringes completely cold. 3. Be able to distinguish between interference and diffraction in a split second. 4. Always double check your units. And 5. Get really comfortable converting path difference to phase difference.
And I'll leave you with one final thought to ponder. If light is a wave, and we know waves bend, why don't we see diffraction patterns all around us, like when light passes through a doorway? Why does it just seem to travel in a straight line? Well, the answer lies in the relationship between the tiny wavelength of light and the huge size of the doorway. Keep thinking and keep preparing.